LabVIEW that probably brought many of you here today. In fact, LabVIEW might have been the product that made you aware of NI in the first place. But there's an even more foundational innovation that allowed you and NI to be here today. And Alex spoke about it earlier today. From the very beginning, when our founders created the first NI GPIB interface, we've been helping engineers to develop automated test systems. Ever since, you and I have been innovating in the way automated tests can add value to the product design lifecycle. To talk a little bit more about automated tests and the innovations that we have in this area, and to share successes of what you are doing, please welcome to the stage Aditi and Avichal. Hey, Aditi.
Hi,
Morning.
Joel.
Morning, Avichal.
Hey, Joel.
Thank you.
Morning, everybody. The simple idea of taking a PC-based instrument and giving it a rugged form factor with integrated timing and synchronization was and continues to be the right idea at the right time. The best choice for us to increase efficiency and reduce cost in automated test is PXI, a modular platform that we invented about 17 years ago. But the true test of a platform is not what it has been able to do in the past, but more of what it is capable of doing. If we are just to believe certain market surveys and reports, it says that the PXI market is about to hit over $1 billion, which is huge when compared to the traditional box instruments. Now let's understand why. PXI represents both disruptive innovation with user-programmable FPGAs and mainstream user requirements like calibration and support. It's these two vectors, disruptive innovation and mainstream user requirements, that I'd like to touch upon today.
Sounds good. Where should we start?
Let's start with production test. Let's have a look at how analog devices use this platform-based approach in their facility.
Handset, wireless communication, and base station. Each of the area requires some level of dynamic performance. There are many standards, and to put all this together in one single part and test it is a significant task. NI's 26.5 gigahertz signal analyzer, I believe, has the RF performance we need for measuring the DAX performance, but also it has the processing power that allows us to reduce the test time and so the cost of test.
When we did performance metrics between the 26.5 gig vector signal analyzer and our existing bench test equipment, we saw about a 30% savings in test time for a lot of the specs that we were testing. We can run more data in an 8-hour day than we could have with other equipment. So that's something that it should help us speed up our evaluation time.
If you use the same hardware, if you use the same software, then you can develop characterization test program and leverage that characterization program for production test. And that is one way you minimize the development cost and, more important, time to market for us. This is where NI can bring a significant benefit to customer.
So we just saw how analog devices has used the PXI platform to replace the traditional ATE box instruments. But analog devices is not the only company. Our estimate is that we have over 700 such systems deployed across the world based on PXI platform. So we saw how they've shown us that they've reduced cost, they've reduced footprint and weight using the PXI-based system. But it's not an easy thing for semiconductor manufacturers to be deploying their own production testers. It requires a lot of time. It requires a group of engineers who can build it and support it. It requires a lot of cost, which most semiconductor manufacturers do not want to do. So what they really need is a platform that can better integrate with their existing production environment. NI offers a huge, massive collection of hardware and software IPs that we repeatedly show making a lot of tough semiconductor measurements. We also have a pool of application engineers who provide services and support across the globe. But one question that we keep receiving from our customers is to provide the capability to better integrate with their existing semiconductor platform. And in that light, I'm really excited to announce the new semiconductor test system that NI has just launched. The NISDS is based on the PXI platform and brings with it the openness and flexibility that the PXI platform has to offer, along with a lot of other features like configuration management, data reporting, system calibration, prober handler integration, etc. So STS currently is available in 3 sizes, depending on the pin and the site count requirements.
So Aditi, I'm pretty sure there's at least one person in the audience that thinks that we just released a turnkey automated test solution. What would you say to that?
Well, with this announcement, NI now offers a higher level of integration, but I wouldn't call it a complete turnkey ATE system yet. So we've been working with a lot of lead users and partners like Reed Ashman and CISO devices to enable our customers, all of you, and our global alliance partner network to come up with these turnkey ATE systems. Also, because the STS is based on the PXI platform, it's both customizable and open for all its users.
Now, you mentioned lead users. So can you tell us about an example where one of these systems is being deployed?
Sure, Joel. Let's talk about IDT. IDT is a fabulous mixed-signal semiconductor manufacturer based out of San Jose. They have their semiconductor production unit in Penang, Malaysia. Now, IDT is one company that was considering PXI for a really long time because they thought the flexibility that this platform offers can help them in using their test capabilities and come up with a semi-custom platform. Also, because STS is based on the PXI platform, it gives IDT the flexibility that they needed in case of increase in performance or increase in their complexities. Because they have their core test platform based on STS, they can continue to reuse and do not have to reinvest in their capital or engineering costs, which they would have had to do had they invested in those big iron ATE systems. So currently, IDT has 3 systems installed are running in their production unit in Penang, and they're looking at standardizing on the STS platform. So this is just one example, Joel, of how STS and PXI has been able to bring down drastically the cost of test.
Well, I think that's a great example and sure a great point on how PXI can deliver on disruptive innovation and at the same time meet the mainstream user requirements. Now, it doesn't take, to standardize on an automated test system, it doesn't take a product like STS to be made by NI. In fact, we have a variety of customers across a large amount of industries that have created their own standard PXI-based systems. Now, one of the advantages of using PXI is the availability of software-defined instruments, software-designed instruments. And actually, 2 years ago, we released our first software-designed instruments, the vector sample transceiver. Now, this software-designed instruments combines the programmable FPGA with the out-of-the-box performance and experience that you would come to expect from a traditional instrument. Aditi, I understand that there's actually 3 software-designed instruments that you're going to introduce to us today?
Yeah. I'd like to start off with this one. If many of you would remember that a couple of years ago, we launched the PXI vector signal analyzer that had RF performance up to 14 gigahertz. I'm really excited to announce that now we've increased that performance up to 26.5 gigahertz. With over 10x improvement in bandwidth, we now proudly provide world's widest bandwidth vector signal analyzer.
I know that, yeah, absolutely. I know that frequency range with that much bandwidth is a big milestone for PXI.
Yeah, and as you may all have guessed, there's a user programmable FPGA that this VSA houses. So that makes it completely software designed. Now I'd like to request Avichal to explain to the audience why user programmable FPGAs are so important.
Well, the great thing about being able to program a user programmable FPGA is that the users can extend the instrument's capability for new or innovative measurements. Now, before this technology, the users needed to add external custom hardware to get this functionality. But with this new FPGA, we can just make some minor modifications to our code and we can get all our algorithms running. But with the custom hardware analogies that the users made themselves, it added to a lot of risk, cost, maintenance, and time. However, it will be best if I can demonstrate the same using some of the demos that I have brought in over here today.
Sure.
Perfect.
So if you could just switch on to the demo screen. Yeah. So actually, communication network providers and government bodies, they'll often monitor or the complete spectrum for any harmful interference signals present in the environment. So I've got such an example of an interference signal over here. If you look at the screen, we are acquiring a 200 megahertz wideband Wi-Fi signal. And then if you look closely, there's also an interfering signal which is phasing in and out of this wideband Wi-Fi signal. So if we are using a traditional analyzer, it will be hard to figure out the source of such kind of an interference. But with the FPGA on the new software-defined instrument, we can reprogram it, we can refunction it to actually debug this issue much easily. So if you just move on to the debug mode of this analyzer, we now see that a real-time spectrum analyzer algorithm has been deployed on the FPGA. And actually, what you see on the screen is the result of 2 million FFTs per second being performed on the FPGA in line with the data coming in. So what we have done is we have taken the intensity and frequency over time, and we have tried to plot it on one single graph. So now we can easily see that the signal that is interfering is actually a chirp at about 5.5 gigahertz.
Impressive. So if I understand that correctly, you were able to customize the firmware of your VSA and then run that new algorithm in line with the measurements?
That's right, Joel. And that is the type of customization that we would request our customers to demand out of their instruments now or even in the future.
Now, Avichal, you also talked about communication networks. Can you tell us a little bit about that?
Yeah, sure. So the mobile communication industry has recently evolved, and it has evolved to drive the need of latest wireless standards and custom protocols inside the same device footprint. So if you could just switch on to the slides now, I'll like to mention that when this whole revolution in the mobile industry, it has led to some challenges in the semiconductor companies. So a typical design engineer would want the maximum performance out of his RF instruments that he is using, whereas a typical production engineer would want lowest test times. Now the problem is that these two requirements are actually conflicting. Now the measurement instrument performance and lower test times are difficult to achieve on the same instrument. However, with the new vector signal analyzer, the software-designed instruments capabilities of the FPGA, it makes it easier for us to correlate the data between design and the production. So if you want, I can show you an example of that.
That'd be great.
Yeah. So what we did was we actually used a 16-bit digital to analog converter, which actually converts digital data at about 2.5 gigasamples per second. So now for this, we required high-speed digital signals. And we actually generated the analog signals out of it and gave it to our new vector signal analyzer, as well as a traditional box analyzer. So if you could just switch on the slide. So the DAC was actually generating the signal into the signal analyzer, the PXI signal analyzer, as well as a traditional box analyzer. So the results that we saw was that both these analyzers were capable of making the measurements, basic measurements like ACPR or adjacent channel power ratio pretty easily. Whereas when we tried to test a sequence of tests on both of these devices, what we found was that the PXI instrument was actually performing 15 times faster than the traditional box analyzer.
Wow. So at this point, the trade-off between measurement performance and measurement speed is essentially gone for microwave frequencies?
Yeah, that's right, Joel. And with this, I have one more product to announce in the same demonstration. Okay. Yeah, so what we have done is we have recently launched a new instrument that we actually used to control and send the signals to this digital to analog converter. So what we needed to send was high-speed digital signals to this particular DUT. So we used our all-new 12.5 gigabits per second high-speed serial instrument to actually generate those digital signals. Now with its 8 digital transceiver lines and the power of the FPGA on this software-designed instrument, we can add any custom or some standard protocol that we would want to generate. So this is not only a new software-designed instrument, it is a completely new software-designed instrument category outside of RF that we have launched.
Fantastic. Thanks, Avichal. Now, if I'm counting correctly, that's 2 new software-designed instruments. Aditi, can you tell us about the third?
Sure, Joel. We're also launching the world's first reconfigurable oscilloscope. Now, the typical oscilloscopes that you see in the market today, let me get that slide right. So the typical oscilloscopes that you see in the market today basically take snapshots of the peak points and then post-process the data in order to identify certain trigger conditions. Now, what happens with this is that there are chances of missing out on certain trigger points, and that makes it difficult for the user to identify the problem, and also takes longer to test. What we've done with this reconfigurable oscilloscope is placed an FPGA right behind the ADC that ensures that the data points are continuously processed and we do not miss out on any of the trigger points.
Now, Aditi, I think that one of the big advantages of having these FPGA-based instruments is the ability to make small tweaks and actually customize the firmware on the instruments to be able to realize much more custom benefits and meet the requirements. Avichal, do you have a demo where you can show us some of this?
Yeah, I do. Okay. So what I've done is I have created 3 pieces of custom IP, and I've downloaded it onto my rear oscilloscope. So what I'm doing is I have applied a real-time spectrum analyzer on my first IP, an NFC demodulator and a decoder on the second, and a custom analog trigger on the third IP. So with, till this point of time in the past, we would have had to use some custom hardware to actually get this functionality. But what now I have to do is make some minor changes in a LabVIEW code, and we are ready to get this functionality out of the box. So now I have 3 demos. So what would you like to see?
Why don't you just pick your favorite and show us?
Sure. So I do have one on the screen right now. So what I'm doing is I'm actually acquiring a lot of signals from my oscilloscope, and it is triggering and getting a lot of waveforms. So if you see, there is quite a bit of irregularity in the signal. If you notice at the top left corner, you can see there is sometimes a glitch which is coming in the signal. So now if you are using a standard edge trigger, it is very hard to single out this particular irregularity. So if you really see, there is a trigger, this green line, that is actually triggering the signal. So even if I try to take it over here, it is not going to make any difference. What I get is the same signal, and I'm not able to single out that particular irregularity. So for this, we needed a more advanced trigger routine. So what we did was we actually created that trigger routine inside LabVIEW, and we dumped that particular routine on the FPGA. So you want to see it working?
Absolutely.
Yeah. So what I have to do is, for that, I just need to create a window on the interest of my signal. So I create an upper bound for the signal, and I create a lower bound for the signal. And what this does is, it singles out all the specific irregularities that I would want in the signal, which I was not able to do now with the traditional analyzers. The reason why this is now possible is because the FPGA on the rear oscilloscope is taking each and every sample and is actually doing the processing on it, so that it does not have any dead times or any missing samples.
Avichal, I think that's a great example and a great use of where you can actually change the firmware on some of these instruments and realize some very significant benefits. Thank you. All right. Talked a little bit about the wireless infrastructure and how that is a key component of the Internet of Things. Now, we've also talked about the proliferation of mobile devices and how many are connected. And as Alec mentioned earlier, by the end of this year, it's predicted that there will be more mobile connected devices than there are people on this world. And just alone, there's already been an 80% increase in the amount of mobile data that's being used compared to 2013. I think this really highlights the need for us to look at our current mobile infrastructure and to start developing a new infrastructure that can handle this capacity. When you add on top of that to the factory future and automation, and more of our industrial systems will start to be connected through machine-to-machine communication in areas like transportation and energy and healthcare, I think this really highlights the need for a new structure. So Aditi, can you talk a little bit about NI's role and how we're involved in looking at some of the next generation of wireless infrastructure?
Sure. So we're working with a lot of lead users across the globe to solve some of the grand challenges that you just spoke about, Joel. But one area of interest that all of us find is the area of increased capacity. Now, everybody in the audience is going to agree with me that we're not happy with the bandwidth on our phones. We're not happy with it on our laptops. So there is a dire need for increase in capacity. Just to give all of you a perspective, in order to be able to meet demand in the next 10 years, we will have to increase capacity to a capacity of 1,000. So that's huge, and the way we'll have to achieve that is with new spectrums, spectral efficiencies, and base stations. While there are many aspects to this research that NI is involved, I'm particularly excited about our role in the work that we've been doing in 5G research.
Can you talk a little bit about that?
So in 2010, NI identified wireless research to be one of the core areas of focus. And ever since, we've been associated with a lot of lead users and leaders in the research market like Nokia. We've also identified and worked with 30 researchers from both industry and academia to build prototypes based on NI's LabVIEW and hardware platform.
And can you tell us a little bit about the recent work that Nokia has done?
So as all of you are already aware, Nokia is a market leader in both mobile phones and wireless infrastructures. So they've been pioneering the 5G research, and some of the research areas are what you can see on the screen behind me. Now their 5G vision is to have high data rate at the peak data rate of 10 gigahertz per second.
Wow. So to put that in perspective, the LTE standard that we talked about earlier today is about 40 megabytes. So 5G represents somewhat of a 300x improvement in speed?
Yeah, about 300 times. So also they've been working on testing the theory of the millimeter wave spectrum, and if that's possible to have dense deployments in cellular networks. There's also licensable spectrum that's available between the 6 gigahertz to 100 gigahertz that they're trying to work on to prove that the communication that happens between that frequency is a viable option.
Yep. What are some of the challenges in proving that those higher frequency ranges are viable for mobile communication?
For obvious reasons, because there's such a huge generational leap between the 4G and the 5G capabilities, they're facing some of the most basic challenges like finding the right hardware platform to actually having a customizable prototyping environment. They were also looking at a flexible and scalable environment. So they did their due diligence and worked around a lot of platforms and got in touch with National Instruments lead user team. And both NI and Nokia have now been able to come out with a 5G proof of concept. And I'm really excited to just mention to you that during NI Week, a couple of weeks ago in Austin, they showed their working prototype of the 5G proof of concept.
Wow, that's quite impressive. Working prototype of 5G. Thanks, Aditi. So, with that working prototype, you guys have talked about quite a bit of information here. You launched the STS for semiconductor test. You introduced 3 new software-designed instruments, the 26 gigahertz VSA, the new serial instrument, as well as the FPGA programmable oscilloscope. I think it's safe to say at this point, if you're considering designing a new test system and aren't at least considering PXI, you're taking a big risk with your test strategy.
Yeah.
Thanks, Aditi.
Thank you, Joel. Thank you.